Okay, hi, this is a video solution for the question 3 in tutorial 3. So this question is about a thermodynamic cycle which consists of the following processes. Okay, so we have learned 3 special processes which are constant pressure, so we'll give it a name as isobaric, isothermal, which is constant temperature, and also constant volume, and we'll give it a name as isometric process. So here you can see a thermodynamic cycle which consists of all 3 special processes, and they will connect one by one and to the start point so that we have a closed loop. Okay, so basically we're going to plot the cycle on the PV diagram first of all. So this is the first question. So as I mentioned actually quite a few times now in the lecture and also in the tutorial in the first week, so the best thing that I would recommend you is that just you need to use a template in the lecture. So if you're still not very sure, you can refer to the lecture slides. So here I'm going to use that template again to plot this thermodynamic cycle consisting of these 3 processes. Okay, so first of all we're just going to plot that template. So this is something somehow you can going to remember the shape of that template. Okay, so first of all we just need to plot x-y coordinate system. So as you can see we have PV. Okay, so this is PV diagram, means that the pressure, okay, the pressure is y-axis, so this is the pressure, and this is the volume. Okay, and in most cases we're going to use the bar for pressure. Okay, and for the volume we have cubic meter here. Okay, so this is our axis PV diagram. So the template is actually just as if you like you're going to plot a small axis like that. Okay, so one is vertical, which is parallel to P, and this one is horizontal, which is parallel to V. Okay, so this represent isometric, this represent isobaric. Okay, and then final one, the final is the isothermal process, which is a curved one. So we're just going to connect here to here. Okay, so this is actually the shape of that cycle is actually fixed. Okay, so just depending on different processes here, so we're going to find out which process, where are these numbers 1, 2, 3. We have 3 corners here with where are they, and also the direction of each processes. Are they clockwise or are they anti-clockwise? So this is actually just what we need to decide. So let's have a look. The first one, 1 to 2, which is constant pressure. Okay, this is because we already plot, the y-axis as P, so x-axis as V. So constant pressure, so it has to be a horizontal line. So on this line, all the pressure has got the same values. Okay, so this constant pressure process has to be the horizontal line like that. Okay, so we just need to find out if this is 1 or if this is 2. Okay, and then this will be decided because for any process we know that this is constant pressure process, but it may go to the right or it may go to the left. Okay, however, the second process from 2 to 3 is isothermal compression process. So we know that's the curved one. Okay, so 2 has to be here. Okay, this is how we're going to plot 2 to 3. Okay, so this has to be 3 actually, because these are 1 and the 2s, so this has to be 3. So if I have 2 here, okay, so 2 to 3 will be just the curved one, which is isothermal compression. So we have 1 here. So if I have 2 here, and then 2 to 3 will not be that curved one. So this is the only way we can have. So actually, once you decide where are these numbers 1, 2, 3, and then you actually just have already found out all the processes here. Okay, so I would like you to plot also the arrows. So this shows clearly 1, pointing to 2, 2 pointing to 3, and 3 pointing back to 1. So we have a closed loop. Okay, so we can also check the third one from 3 to 1, 3 to 1, which has got the same value of volume, so what is called a constant volume process. Okay, so basically you have plotted all the processes on this PV diagram, and what you can do now is that actually you can put all these values if they have been given. I mean all the P values, V values for the state number 1, 2, and 3. Okay, we'll have a look. For the first process, 1 to 2 constant pressure, so the pressure P is 1.5 bar, which is for P1 and also for P2. So here, okay, this is 1.5 bar for P1 and P2. And also we have V1, so 1 is here. So V1 is here, which is equal to 0.025 cubic meter. And also we know that the work done during 1 and 2. Okay, so we definitely need that to solve some unknowns later. Okay, so basically we already add all the information which will be given on this PV diagram. Okay, so this is the first step, sketch the cycle on a PV diagram. Okay, let's have a look at the second question, which asks us to calculate the net work transfer during the cycle. Okay, because we have this cycle, we have 3 processes, so we need to calculate the work done for each process, and then we'll add them together. Okay, so this is how we call it the net work transfer. Okay, so the easiest way may actually be the work done from 3 to 1. Okay, this is because 3 to 1 is an isometric process. So if we have a look at the formula sheet, okay, so we have 3 equations here. They are used for calculate the work done. So the first one is for work done. This is quite a general form, so you can see here. Okay, the work done is equal to the P times dV. We do the integral from 1 to 2. So for any isometric process, you can see isometric process, okay, such as 3 to 1. That's because we have a constant volume here. Okay, this is volume, so constant volume means that the change in volume is 0, means that dV is 0. Okay, so that's why the work done for isometric process is actually 0 here. Okay, so first of all we can write actually the work done, okay, 3 to 1, because this is the easiest one. Okay, is 0. This is because this is isometric process. Okay, so now we're going to calculate the work done for 1 to 2. However, this is actually being given work done for 1 to 2. Okay, so we're going to use that to calculate something, which has not been given. If we write that equation, W1 to 2, so 1 to 2 is an isobaric process, which is a constant pressure here. So we'll look at the formula sheet again. Actually, the second equation is for isobaric process. Okay, so the work done is equal to P1 or P2. That's because they have got the same value. And the change in the volume, V2 subtract V1. Okay, so we're just going to write that equation, P1, V2 subtract V1. Okay, now we're going to put all the values inside there. The most important here is that we're going to convert the units as necessary. So the easiest way, as I always recommend you, is that if you are confused, you just convert everything to SI based unit. But first of all, you need to be very clear about what are these SI based units for different variables. Okay, so for the work done, Okay, the SI base unit for work actually is joule, but however we sometimes, or actually quite often, we're using kilojoule. Okay, because the joule is a too small unit. So if we want to use this figure here, so we're going to convert a kilojoule to joule, which is SI base unit for work. So on the left hand side we have 12.5, so we need to times 1000. Okay, pressure. So pressure for 1 here is 1.5. You can see the y-axis is a unit of a bar, and bar is not SI unit, so we need to convert that to Pascal, which is SI base unit, by times 10, 5 as a power, okay, times V2. V2 here actually has not been given. This is why we need a V2 to calculate the following questions. So it's subject V1. Okay, V1 has actually been given 0.025. Right, okay, so we're just going to rearrange them. So I'm going to move this one over to the left. Okay, basically I'm going to divide. Okay, so once you calculate this one, you also move 0.025 over to the left as well, and then you can calculate the value of V2, okay, which is 0.108 cubic meter. Right, okay, so this is how we're going to calculate the V2. Now we're going to calculate the work, because I said in order to calculate the net work transfer, we need to calculate the work done for each of these processes. So this is 1, 2, and 3. We're going to calculate this one. So this one is the last process, actually, from 2 to 3. You can see this is a curved one. So 2 to 3. Make sure we have the starting point, end point. So the curved one represents an isothermal compression process. So we're going to have to check in the formula sheet the work done for an isothermal process. Okay, so we have P1V1, P2V2. They are the same because for an isothermal process, PV is a constant. And Ln V2 over V1. Be careful. On the top we have the end point. So 1 to 2, 2 is end point. Okay, and end point should be on the top, V2 over V1. Okay, so you need to be very careful about all these subscripts here. So in this case, we'll go to write the work done for 2 to 3. Then we have P2V2 or P3V3. Okay, on this curve, they are the same. So I'm going to use P2V2 here. Ln V over V. So be careful, as I said, this is end state, end point, which is 3 here, over V2 here. Okay, so now I'm going to write P2, which is 1.5 bar. Again, we're going to convert that to Pascal times V2. So V2 is here, 108 times Ln V3. Okay, let's have a look at this diagram. How about V3? V3 is actually V1, so they're the same because this is a vertical line. So we have got V3 same as V1 over V2. Okay, so you just need to use your calculator, and the answer is minus 23.7 kilojoule. And then we can calculate the network. Okay, so the network is just the sigma. So we need to add 1, 2, and 3 altogether. So the first one, 0. The second has been given here. Okay, 12.5. third is here. Okay. So that's the answer for the network, right? So we have the third question here, asked to calculate the heat transfer. So the heat transfer 1 to 2. So let's have a look. Where's 1 to 2? 1 to 2 here. Okay. So this is a process. We're going to calculate the heat transfer during this process. So in this case, we're going to use the first law of thermodynamics in closed system. Okay, this is because from this equation you can see that we have some relationship between Q, the heat transfer, and the work transfer, and the change in delta U. Okay, so for the first process, for this process of 1 to 2, the work transfer has been given here. Okay, so we need to calculate the heat transfer. So we're going to use that equation. So first of all, I'm going to write here. Okay, so this is the second question, and this is the third one. Right. So first of all, I'm going to write Q subject W. Okay, I'm going to write that equation. You have to be careful about. This is U2 subject U1. Okay, so you can see W1 to 2 has been given here. Okay, then we need to find out U2 subject U1. So however, if we have a look here, all the information, we can't directly find the difference between U2 and the U1. However, we have these two. Okay, so we just need to make a use of these. So this one, U1 subject U3 is minus 28.2, and also have to have U3 equal to U2. Okay, in here U3 is actually the same as U2, so we can just replace U3 with U2. Okay, as you can see on the right we have U2 subject U1, and this is U1 subject U2. Okay, so this is actually the root. So we get here, we just swap it, so we can times -1 on both sides, and then we get okay. So actually we found U2 subject U1. Now we can just move Q1 to 2, we move W over here. W1 to 2 is 12.5, so that's in kilojoule, and so you can see here kilojoule as well, so this is in kilojoule as well. Okay, kilojoule, and then we'll just add them together, which gives us 40.7 kilojoule. Okay, so this is the value for the heat transfer, which is our third question, the heat transfer during the process from 1 to 2. Okay, so this is all the solutions for question 3.